In this lecture, we'll be dealing with formal charges and resonance. These are the last two basic topics of covalent bonding, and the use of these two terms topics are tied to the higher level diagrams, the Lewis dot diagrams that can have multiple forms. That's right, there are going to be some types of Lewis dot diagrams that we can write in many ways. Formal charges is a way for us to decide if we can write a Lewis dot diagram multiple times that's correct by all of our rules, okay, which one's the best. Resonance is going to show us that some structures resonate between different structures. They go back and forth somewhat, or is a mixture, and these are exclusively tied to each other. So let's start with formal charges. As we've done already, okay, we have looked at formal charges, and basically formal charges are the idea that we get to figure out which atom or which structure is the best by looking at the individual charges. Formal charges are basically an analysis of how the valence electrons, the electrons they have, actually compare to electrons they use, okay, in a Lewis dot structure. If you have 5 valence electrons that you have from your atom, and you write them into your structure, and you use all 5 exactly, your formal charge is 0. Now, assigned electrons are all non-bonding electrons, and half of your bonding. These are these essentially represent the electrons you use. I'm not big on this formula. I like looking at them. For instance, as we did already in class, nitrogen is using total in this example 2, 4, 6, 7. Okay, that's why it's 6 plus 1 here. 6 of its lone pairs plus half its bonding is 7, and it comes with 5 valence, so 5 minus 2 is a negative 2. And that's why this has a negative 2. This carbon has no lone pairs, so it's only assigned 4, which is half its bonding. 4 valence, 4 it's using. It has the best number, 0, meaning it's using exactly what it's given, which makes a lot of sense in nature. Carbon's going to hit nitrogen and probably use the electrons it has to make the structure. It's not going to gain or lose. In this case, nitrogen being negative 2, it says it gained 2, okay, to make it work. Sulfur, all of its lone pairs, which is in this case 2 right here, plus half the bonding, gives me 5, right? And it has 6 valence. 6 minus 5 is plus 1. So what we're saying here is sulfur lost an electron, okay, and it was given to the nitrogen. What does that mean? Well, the chances of nitrogen gaining an electron from sulfur crossed, okay, through carbon to make this work is a pretty low probability. So a negative 2, 0, and plus 1, this negative 2 is a red flag, too big, okay? And this one real quickly gives me a negative 1, 0, and 0. Of course, carbon is using exactly what's given, so is sulfur. This has 6 it's using. That means it gained 1 from the environment. That's why everything equals negative 1. And of course, we have 0, 0, negative 1 here. Sulfur is showing that it gained 1. Now, the best structure, as we talked about in class, okay, is this structure because it has the lowest numbers in terms of closeness to 0, the less movement of electrons, which is probably the most reasonable. And of course, the negative is on the more electronegative atom. This one had to gain 1. It makes sense. So this was the best structure. And this is what we did today. Now, moving on, okay, we have the next question is draw the Lewis diagram for NO2 nitrous oxide or laughing gas. So we're going to move to the digital file to do the Lewis dot diagrams, the 3 basics that can occur, okay, and then go on to formal charges. Okay, so here we have N2O, nitrous gas. N2O is sometimes called laughing gas. So N2O, 2 N's and an O bonded together. So let's figure out the structure here. So you'd put out all the valence electron. Each N has 5, each O has 6, and as if you were to do this pencil and paper, you should throw out the dots. Pencil and paper makes it easier. Okay, I'm circumventing that by using this digital drop and drag, okay? Any case, So I have all my valence electrons out, and I'm going to do one bond here. Okay, well, if I do one bond here, I know nitrogen likes to make triple bonds, so let's think about here. I'll put a triple bond maybe. Okay, I know this is 1, 2, 3, 4, 5, 6. Nitrogen needs to have 7. Okay, need 8. So I'm getting this structure. If you notice, oxygen has 2, 4, 6, 8, 9. So this is the structure I can get here. Okay, so everyone has 8. This guy has 8. The middle nitrogen has 8. Okay, and this is following the octet rules. Is this a possibility? We're going to have to use formal charges to find out. So let's do some more. Okay, so I did a triple bond on that side. Let's do a double bond on this side. So here's a double bond. Double this up. Okay, and here we go. And I guess we're going to have to do a double bond over here because nitrogen has to have 8, 2, 4, 6, 8 for the oxygen, 2, 4, 6, 8. And if you notice, this nitrogen, 2, 4, 6, 7, it needs one more. 2, 4, 6, 8, 2, 4, 6, 8. All right, it's the other structure. Now, we had a triple bond on this side. Why not? I'm going through all the possibilities. All I'm doing is following the octet rule. All these atoms are in the second row. Okay, and this would have to be a single bond. All right, and there we go. This oxygen has 8. This nitrogen has 8 by sharing. They all have 8. And these are the 3 structures. And who's to say one is better than the other when you consider the fact they all have the octet rule, or all are satisfying the octet rule? Well, formal charges comes to the rescue, and it helps us figure out clearly who's the best structure, or in this case, what we think is the best structure. So this end, okay, is assigned 2, 4, 6, 7. It brings to the table 6 and 5 valence electrons. So 5 minus 7, negative 2. All right, this nitrogen has 4 assigned to it. So that's 5 minus 4. That's a plus 1. This oxygen starts out with 6 valence, and it's only assigned 5, so 6 minus 5 is also plus 1. Okay, you notice the whole thing equals 0 here. There's no charge. The other one had a charge. So this means there's something here. But this negative 1 here, negative 2 here, I'm not liking. If you notice, 2 different colors, this had to gain 2 to make this work, especially 1 from the oxygen. Highly unlikely this is going to happen. But let's continue. This nitrogen, okay, starts out with 5 valence. I'm subtracting 6. 5 minus 6, negative 1. This guy right here is only assigned 4. 5 minus 4 is plus 1. Okay? Well, it's a little better, I think, because it doesn't have that negative 2. And this oxygen is assigned 6. It has 6 valence, so it's 0. Now, the assigned is easy. All the lone pairs, in this case, this N had none, half of its bonding 4. This had half of its bonding, which is here, and all of its lone pairs 6. This N, so this is a 0, and this is a better structure because I have lower numbers and I have a 0 popping up, which is better because this means that this oxygen made this compound by using its electrons, and these guys had less movement. Okay, this nitrogen has 5 valence electrons. It's assigned half its bonding, which is 3, plus its lone pair, it's 5. This is 0. This nitrogen's bringing all of its electrons to the table and using exactly what it brought. This is a strong possibility already. This nitrogen has half of its bonding and its lone pairs. No lone pairs, so it's 1, 2, 3, 4. So this is 5 minus 4 plus 1. This plus 1 means it kind of lost 1, right? You can see that it's kind of given 1 to the oxygen. Oxygen is half of its bonding plus its lone pairs, 1, 2, 3, 4, so I drew this poorly. So 1, 2, 3, 4, 5, 6 plus 1, 7. So 6 minus 7. 6 is the valence electrons it brings. 7 is what it's assigned with. So it's negative 1. Okay. So clearly to me, I can toss one out. Okay, right from the get-go here. And I'm going to toss out this guy right here. That negative 2 and plus 1 and plus 1 are giving me too much movement. Electrons have to be passed around too much to make this sharing work. So that's why I'm going to toss it out. Unrealistic for that to happen. So now I'm down to these two scenarios. Which one's better? Well, I have a negative 1 on the oxygen, and I have a negative 1 on this nitrogen. So if I was to say what was the best one, you would have to say, based on what I've taught you, that this is the best structure for N2O. And you'd be correct. And a lot of times on an AP or a highly advanced chem course, you'd say, what's the best structure using formal charges? And this would be it. But I want to show you something, that we're getting to the end of our, or the limits to our valence bond theory here. And the limit here is that this formal charges, these Lewis dot diagram, hybridization, all great, tell us a lot of information, but sometimes doesn't match exactly what we find. And that's why we need other theories like MO theory in AP. But so this formal charge suggests that this is the answer. Data revealed, okay, when you measure this compound, reveals that both structures actually occur. Now, I won't ever ask that of you. If I was to ask you on a test which is the best structure, you go by the rules. But in truth, both of these structures actually do exist. And I want to explain that. Okay? If you look here for a second, these are the two structures that we said was the best. There's the triple bond between the N and the double bond between the N. If you go back, there's a triple bond between the N and a double bond. Okay? And these are the best structures. Okay, now what does that mean? It's a mixture, okay? Actually, these two structures actually resonate between back and forth. I mean, there isn't really a triple or a single bond, and I'm going to explain that a little bit in a second. But let's go to here again. Maybe not. Let's go back to this one. All right, and I guess I have to go back even further. So what's happening is these are going back and forth. They're resonating. Resonating. Now, what does resonating mean? Resonating means that these compounds don't have this structure, and it really doesn't have this structure. They have a structure in between. And I'm going to pull up another page to show you something. Okay, so we're back here on the same this is the actual key that you have linked. And here are the two structures that we said were the best. Now we know that one was better than the other based on formal rules, but I want to show you where the evidence is leaking in to show us there's some limitations. Let me explain. A single bonded N, okay, to another N is 0.46 nanometers. These are bond length data. Now a bond length really suggests strength. If two atoms are really bonded strongly, their bond lengths are shorter. If something is weakly bonded, it's farther apart. Think of the nucleus. If a nucleus is attracting electrons in a covalent bond, in a strong bond, these nucleus will pull in these electrons together, okay, and actually make, okay, the bond shorter. A weaker bond is a longer bond. It's pretty self-explanatory. So the shorter the bond length, the stronger the bond. When they break this compound up and measure the bond length, okay, in an independent evaluation, remember, we're just dots on a paper. Here's what we get. A single bonded is 146 nanometers. A double bond is 1.25, and a triple bond between the ends is 1.10. They actually measure the bond between the nitrogens to be 0.113 nanometers. That's in between a double and a triple bond. That's troublesome. How can that be something in between? Either have a single, or either have a double or a triple. A triple bond is going to be shorter. Well, this isn't short enough to be a triple bond. It's a little longer, so it's a little weaker than a double bond. I'm sorry. It's 1.13, okay, is longer than a triple bond. So it's a little weaker than a triple bond. And because it's much shorter than a double bond, okay, it's stronger than a double bond. I'll say it again. If the bond length is 0.113 and the triple bond is 0.110, stronger bond has a shorter bond. So this end-to-end bond in the actual compound tested is a little longer, thus a little weaker than a triple bond. But it's stronger than a double bond. So it's somewhere in the middle, which is telling us that this double bonded N or this triple bonded N in our diagrams, here's a triple bonded N or the double bonded, is somehow, some way in between what we expect. So we say these structures resonate, meaning there's a mixture. These two structures mix. Now, again, I wouldn't expect you to know that. All I expect you to do is be able to tell me the best structure. So very simply, this is an example of resonance. Okay? We know the best structure based on formal charges, but the theory kind of breaks down because there's some data suggests that the best structure is a mixing of the two. The mixing of two orbitals is called resonance. It doesn't mean they're both, they're somewhere in between. So as it says, our rule suggests that this is the best structure, negatives on the more electronegative atom. Okay, right. But experimental data shows that there's a blending of the two. Okay? So when we show resonance, we show a double arrow to show that it's a blending of the two. So this is the correct way to show the resonance between the two. Double arrow and show both structures. Okay? Now, what's interesting, or maybe not be interesting, is that this resonance actually makes this molecule nonpolar. Most of the polarity, okay, this is more electronegative, you'd think this is the negative end here. But because these electrons somehow blend back and forth, this blending of electrons back and forth, we call them delocalized electron. Delocalized, I can do this. I'll do it. Delocalized electrons that are blended on top that make this sort of a double, sort of a triple, okay, actually make this structure nonpolar, and that's why it's used as a gas in whipped cream to accelerate the cream out of the can. Okay, so that's one of the reasons why they use N2O. It's a laughing gas, okay, and it affects the neurological system because it's nonpolar. It can get to the gray matter, which is mostly nonpolar in our brain. So in any case, very interesting enough, that's what happens here. Now, okay, so what's going on here? Let's draw, guess what? These lovely illustrations to show you. What is making this resonate? All right, well, let's do it. Let's move this guy over here. Now notice, we're talking about central N. It's bonding to two things, so I'm guessing it's sp hybridized. So because the N and the O are on the what? On the outside looking in, or we say terminal, they're unhybridized. So I'm going to put in the valence electrons, okay, for the middle nitrogen. So here's one. Here is the other. Okay, and I'm showing you how it's a blending of both here. So I know there's 5 valence electrons. Okay, they could be 3 or they could be 2. So I'm going to put electron here, and I guess I'll put electron here. So 1, 2, 3, 4, 5. All right. Now, the nitrogen also has 5. Here's 1, 2, 3, 4, and we'll do 5. Let's see if we want to do that. Okay. And then we'll do the other oxygen. This one has 6. 1, 2 in the S. Oops, keep that there. 2 in the S. 1, 2. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. This one's filled. This one's not. Okay, and I might have to move these around. So let's see what we have here. We have the first bond, which is definitely stable. Okay, that's the bonds here. That makes sense. How do I get 2 bonds on this side? Well, we have to have some ability to pi bond. So you may say, okay, well, this one's filled, this one isn't. Okay, let me try moving this around to make some sense of this. Okay, so how do I add the second bond? Well, here's what could happen. Who's to say this electron could jump here? Okay, and if this electron jumps here, that leaves an opening. Okay, and who's to say this electron can jump here? This electron's in the same plane. It can move down here, and this one can move over. And you notice we've got a blending of bonds between the unhybridized, the unhybridized P's. And that's how this usually resonance can occur. Okay, I can go here, I can go here. These electrons are allowed to move throughout the same unhybridized P's. Okay, and that's what causes the idea that you can have these bonds. Hey, this one can bond here, back and forth, and this one can move here. So because you have unhybridized P's that have openings, these electrons are mobile and can become delocalized over different atoms and cause the multiple bonds. That is what I'm talking about here in resonance. Okay, so the bottom of the page, we have NO3 to do. Okay, and let's just draw that instead of dragging it. I have an N, I have an O, I have three O's. I'm doing a Lewis dot diagram. And I put out the valence electrons. 1, 2, 3, 4, 5. Oxygen has 1, 2, 3, 4, 5, 6. This has 8. This nitrogen has 1, 2, 4, 6, 7. Well, I'm going to draw this oxygen with 6. I'll draw this one with 6. I can't really add any double bonds here because nitrogen already has 7. It needs one more. If I move one over, this one still needs one more. So believe it or not, this guy, just like we talked about today in class, is going to get one from its environment. So let's draw a triangle here. This electron was gained from the environment, maybe a metal, to make all this work. Now this nitrogen feels like it has 8. Okay, this oxygen feels like it has 8. Everyone has 8. This whole thing is -1 because it grabbed an electron. This is called a nitrate ion. And it has a -1 because it gained one to make this covalent bonding work. Now, very understanding what's happening. Let's bring our formal charges into play here. Okay, this one has a 0, right? 6 minus 6, if you look at half of its bonding. This has a -1, right? It has 6 minus what? 7. Okay, and I'll do that slower again. This 6 minus 6, this has half of its bonding, and it brought 6 to the table, so it's a 0. Here, it's half of its bonding, and it's lone pairs, so it's 6 minus 7. That gives me the -1. And here, half of its bonding, oops, I didn't do that right, half of its bonding here, and it's 6, so 6 minus 7, -1. What is nitrogen? Well, nitrogen is half of its bonding. There's no lone pairs. So it's got 1, 2, 3, 4. 5 minus 4 is +1. So we've got plus -1, 0, -1, and +1. These numbers give us the -1 we need. So, what does this structure look like? Let's draw it nice and neatly now. We have nitrogen with a single bond to an O, double bond to an O, lone pair is only 2, single bond to an O, got to show the 6 lone pairs. I draw a bracket because I'm polite, okay, and I'm -1. Am I done? No, I'm not done. Well, why can't I draw this? Why do I have to keep the double bond in one place? Let me explain. Why can't I draw this? The double bond over here. Let me explain. What's the hybridization here? sp2. How many unhybridized P's do I have? 1. And that unhybridized P goes through the middle and allows for the electrons to go back and forth and resonate. Sometimes people will draw it like this and draw a dotted line to show that. Okay, so to draw this, you'd have to throw 3 structures with arrows going back and forth. Okay? So this is the best structure right here. Okay, these 3 structures are resonating back and forth. Does it mean that the double bond is here and then here and here and moves back and forth? No, it's mixing, it's blending. And a great picture to show you what's happening is this sp2 hybridized trigonal planar. Look at that. This is the O over here, so it's in a trigonal plane. Look what it's showing you. These unhybridized P's that are sticking up through the center are all in the same plane, and these electrons are able to move above and below the molecule. And that shows you the resonance. It's not really a double bond, it's something in between, like a 1.3 bond. All these bonds are the same, but they're somewhere in between a single and a double. It's because these electrons are free to delocalize all over because of that, what? Unhybridized P that can allow it to move. Okay, so what I'd like you to do for homework is I would like you to do O3, okay, and CO3 negative 2 on the opposite side. Try to do those. They do have resonance. Give me all the correct structures. Thanks for playing.